Welcome to this explainer. Today, we're stepping into what I really like to call the AI prep kitchen. We constantly hear about how artificial intelligence can cook up these brilliant insights and solve massive problems. But here's the reality. Before an AI can actually do any of that, we have to prepare the ingredients. And in the world of AI, those ingredients are raw, messy, totally chaotic data. So think about this. Why do some incredibly advanced AI models just completely fail or take days to run without giving us a good answer? Well, feeding an AI massive, raw data sets is literally like throwing unwashed, unpeeled, whole vegetables directly into a frying pan and expecting a Michelin star meal to just magically happen. It really doesn't work. The AI, just like the pan, simply gets bogged down. And that brings us to our core topic today: data preprocessing. This is the invisible, completely unglamorous, but absolutely crucial prep work of cleaning, measuring, and transforming our raw data into a format the AI can actually digest. It's the foundational step where we substitute and scale our ingredients so the algorithm can run efficiently. So, here's our kitchen prep checklist for today. Step 1, standardizing the scale. Step 2, sorting and grouping data. Step 3, shrinking and sampling. 4, summarizing the noise. And 5, cutting the clutter.
Let's dive right into step 1, standardizing the scale.
Before we manipulate anything, we have to figure out what kind of ingredients we're working with. Basically, identifying our data types. Is your data nominal? That means it's from an unordered set, like a list of colors or professions. Or is it ordinal? This is data from an ordered set, like academic or military ranks, where there's a clear hierarchy. And finally, is it numeric? These are your standard real numbers or integers. Once you know exactly what you're holding, you have to scale it.
Think of normalization kind of like converting currencies. How does an AI compare an income of $73,000 to a person's age of 35? It literally can't, unless they share a scale. So if we have an income range of $12,000 to $98,000, min-max normalization maps that entire range proportionally between 0.0 and 1.0. So our $73,000 becomes 0.716. The z-score method uses a bell curve. It measures the distance from the average using standard deviation. If the average is 54,000, our $73,000 maps to 1.225. And finally, decimal scaling just moves the decimal point, mapping it to 0.73. This whole process just ensures all our different ingredients are speaking the exact same mathematical language.
Moving right along to step 2, sorting and grouping data. Now, data scientists use a highly technical-sounding word for this. They call it discretization. But let's bust that jargon immediately. It really just means taking a smooth, continuous line of numbers and chopping it into distinct, chunky intervals, or buckets. By replacing a million complex actual values with just a few simple interval labels, we massively reduce our data size. Imagine equal width partitioning as a uniform grid. It's basically a perfectly spaced bar chart. The math here is beautifully simple. You take the highest value in your dataset, subtract the lowest value, and just divide by the number of buckets you want. You do have to be a little careful, though, because extreme outliers can sometimes distort this neat presentation. All right, let's look at step 3, shrinking and sampling. What happens when your data warehouse has literally terabytes of data? Complex analysis just takes way too long to run. We have to shrink the footprint of our ingredients without losing the flavor of our dish, and we do this through sampling. Let's contrast two methods. Sampling with replacement means you pull a data object out, analyze it, and then throw it right back into the mixing bowl to potentially be picked again. Sampling without replacement means once an object is selected, it's removed from the population entirely. But when you're sampling, there is one golden rule. You must choose a representative subset of the data. If you just scoop a random handful off the top, it might perform terribly, especially if your data is heavily skewed toward one type of outcome. You need smarter, adaptive methods. And the absolute best adaptive method is called stratified sampling. Think of your data like a giant layered cake. If you just scoop off the top, you're only tasting frosting. Stratified sampling means partitioning the data into its distinct layers or clusters, and then taking a proportional slice from every single layer. This ensures you get approximately the same percentage of data drawn from each category, giving you a perfect taste of the whole cake. Another way to shrink data is compression, which comes in two main flavors. Lossless compression means you can reconstruct the original data perfectly, but it only allows limited manipulation without expanding it back out. On the flip side, lossy compression, which is typically used for audio or video, actually drops small fragments of the signal.
It's not perfect, but it allows for progressive refinement and massive space savings.
Okay, on to step 4, summarizing the noise.
This step is actually known as numerosity reduction, where we reduce data volume by choosing alternative, much smaller forms to represent our data. And we have two main families here. Parametric methods assume the data fits a certain mathematical model. You figure out the parameters of that model, store only those mathematical rules, and literally discard the actual raw data. Non-parametric methods, on the other hand, don't assume a strict math model to start with.
Let's look at parametric methods first. Linear regression fits your massive dataset to a simple straight line. Instead of storing millions of individual data points, you just store two simple numbers, the coefficients that draw that line. We also have multiple regression for multidimensional data and log linear models. By keeping the recipe's mathematical formula and tossing the raw ingredients, you save an immense amount of space.
Now, on the non-parametric side, a really major method is clustering. Here, instead of assuming a line, we group similar data points together into clusters. Then, instead of storing the data for 1,000 individual points in that group, we just store the center point, which we call the centroid, and the diameter of the group.
And finally, step 5, cutting the clutter. In data science, there is this terrifyingly named concept known as the curse of dimensionality. Basically, when you have too many attributes, say thousands of different features you're tracking, the data becomes increasingly sparse. The distance between points becomes way less meaningful, and it actually breaks our clustering models. So we have to extract a smaller set of principal variables. We solve this issue with feature selection. Think of it like packing a suitcase for a weekend trip. You don't need 3 heavy jackets that duplicate the exact same function. That's a redundant attribute. You also don't need to pack a toaster. That's an irrelevant attribute. Feature selection systematically eliminates the duplicates and the useless clutter, so the AI can travel light.
But what happens when feature selection isn't enough? Well, we use a brilliant technique called principal component analysis, or PCA. Imagine 3 different cameras all tracking a single ball traveling in a straight line. Those 3 cameras contain massive redundancy. PCA is a mathematical transformation that takes those correlated variables and projects them onto a much smaller space, turning them into a tight set of uncorrelated principal components.
Here is the exact 4-step recipe for PCA. First, we normalize the input data, which, if you remember, was our very first step today. Second, we compute the principal component vectors. Third, we sort those components by decreasing significance or strength. And finally, we eliminate the weak components with low variance. We're just using the strongest components to reconstruct a really great approximation of the original data, but at a fraction of the size. Which leaves us with this thought to end on. We've seen exactly how we scale, chop, sample, summarize, and cut the clutter of data. Data preprocessing is clearly the invisible secret sauce behind every single successful machine learning model. But it makes you wonder, if an AI's so-called intelligence depends almost entirely on how meticulously humans prepare the ingredients beforehand, who is really doing the cooking? Thanks for joining me on this explainer. I'll see you next time.